Thank you. So my name is Dalia Popescu or Herculea, and together with Philippe Jacquet here, we have a work called Self-Similar Geometry for Ad-Hoc Wireless Networks, and we introduce a model called hyperfractals. So our work shows that actually wireless networks, and in particular in this case the ad-hoc wireless networks, can be deployed using Poisson process that are following a distribution with scaling properties. In particular, today we're going to talk about a distribution following hyperfractal scaling with a dimension superior to the dimension of the embedding space. That's why we call it hyperfractal. Furthermore, to make clear the contrast is that fractals are objects, sub-ensemble sets. I don't know what happened. Okay. While a hyperfractal is a positive measure. So let us define this object. So, okay. So if I want to define the hyperfractal, I would say that it's a Poisson shot model which has a support, a measure whose fractal dimension is higher than the Euclidean dimension. In this case, we're going to work with the Euclidean dimension 2. The density on mobile nodes on lines will decay as a function of the street level, and we're going to build the hyperfractal as we usually do with fractals in a recursive iterative process, like it follows. We begin by drawing a central cross on the plane. On this cross, we place mobile nodes with probability p prime. What remains, the complementary probability, we call it q prime, and we were going to split it equally in 4 in each of the quadrants. Therefore, the probability to place a node in each of the quadrants is q prime over 4. Furthermore, we go to the next step, and we iterate again, and in this step, again on the central cross of the quadrant, we place the node with probability p prime multiplied by what it was rest, q prime over 4, and that's how we keep on going into iterations. So following this process, the actual density of a street of level h, we start by level 0, is p prime over 2 multiplied by q prime over 4 at the level h. I'm going to draw your attention here that the density is decaying, again, is decaying with the level of the street. So let us go further. How do you compute the fractal dimension? Just as usual, like we do for the Sierpinski triangle. So we see the weight in halving the distance is q prime over 4. So we obtain this expression, the fractal dimension of the support measure, which is higher than 2. So if you're wondering, how can we have a dimension that is higher than 2? Well, this is because we do not have a set, but a measure. And the measure is a concept that is insensitive to dimension. And as an example, you can think about R1000, which is in Lebesgue bijection with R2. So now let's pass from the concept of measure to our application of wireless ad hoc networks. And we're going to think in particular to the application of wireless networks in urban environment. So in urban environment, the architecture of the cities is influencing the signal propagation strength. Buildings that are built by concrete and glass do not let the signal propagate out through the buildings. Therefore, mobile nodes are obliged to communicate only with mobile nodes placed on the same street. As you can see here, the heat map of the signal strength on a city. This gives the fact that the connectivity of the network is limited. So, to solve the problem of connectivity, we're going to add relays, and not in any way, but according to another hyperfractal process. So, we start by splitting the plane with a line, and on this line we place the relay with probability p, and in each of the obtained half planes we q over 2. Let's say we do the same from the other side, and with a vertical line, this time we split the plane in 2, and we put the relay with probability p on the line and with q over 2 on each of the half planes. If we combine the both, we obtain that in a crossing we have a relay with probability p square, and each of the quadrants with q just a second, Q over 2 square. And furthermore, this time, we can compute also the probability of having a relay in each of the segments. We're going to say segments because our map is limited. So again, we will go further and further in iteration, just like we did in the hyperfractal, and obtain an object with a level that goes towards infinity. Again, we can compute the fractal dimension, similar as we did for the fractals, and we obtain a number that is again higher than 2. So again, we have a hyperfractal dimension. Furthermore, we can consider that the number of crossing selection runs, the Poisson process with a random variable of mean rho. And we're going to denote by P of H of V, just an example, the probability that the run selects a crossing of a street of horizontal denoted by V, H, and a vertical one with the level V. So if we are to compute the number, the average total number of the releases in the CP, this variable, we're going to make the summation of all possible vertical and horizontal levels of all the possible crossings in the street, multiply the probability of existence of a relay in that intersection. And happily, this summation goes to the infinite, so we get an expression that has a scaling with the fractal dimension of the relay process. I give you here an example of what we obtain if we run this process is starting with 500 points and with fractal dimensions for nodes and relays being equal to 3. So in red you have the relays, and in black the hyperfractal nodes. As you can see, the central cross is the cross that is most dense in both mobile nodes and both relays, and that's why we're going to start our main results, our main theoretical results from there. The analysis on the giant component, the component containing the central cross. So here it goes. This is a theorem saying that the fraction of mobile nodes in the giant components will tend to 1 when the seed of the Poisson process, of the process generating the relays, tends to infinity. And furthermore, the fraction of the number of mobile nodes outside the giant components, we can compute it, and has an expression function of the fractal dimension of the mobile nodes and of the fractal dimension of the relays, again when rho goes to infinity. So sketching a bit the proof, we're going to start, just an example, with a horizontal line. Might as well we can start from a vertical line. So we can compute the probability of this line being connected to the central cross, just as we did earlier. And we have this expression. I will remind you that the density of mobile nodes on each line, we have the expression, it's a function of the level of the line. And furthermore, we have 2 of each lines connected to the central cross. I will specify that there are 2 of each lines connected to the central cross, horizontal lines, and through a single relay. Furthermore, if we want to see the cumulated density of these lines, I'm talking the density of the nodes, we're going to make the summation over all possible horizontal lines, the probability, the density of this kind of lines, and the probability of being connected with one single relay to the central cross. Again, we've been talking about horizontal lines, but we have to take in consideration the vertical lines as well. Well, we said we are interested in the number of nodes outside the giant component. So in order to compute the number of nodes outside of giant component, we're going to look what we obtain by taking out this quantity. So we can think about the quantity which I will denote by E of rho being, if you want, the density of the nodes outside the giant component, from the whole density of mobile nodes in the network. We're going to take out this quantity, that is the density of the nodes on lines connected through a single relay to the giant components, and furthermore 2 of P, which is just the density of the lines on the central cross. So this is just an upper bound. And happily, the expression is a summation that goes to infinity, because we have a fractal and hyperfractals, and hyperfractals are objects that exist towards infinity. So we obtain a nice expression, which is a harmonic sum, on which we can apply the Mellin transform, which is very beloved here by Philippe Jacquet. And this Mellin transform has a simple pole. Again, we're going to apply the inverse Mellin transform, and we obtain the central result of our paper, saying the mobile nodes outside the giant component. So once we saw that the object has nice connectivity properties, we can see how we can use it for mobile networks again. So we're going to look how we do the routing on this kind of an object. We're going to consider two routing strategies, one which is the nearest neighbor routing, so it's just hop by hop from one node to another, and another one that is the minimum delay routing, well, which you might be using Dijkstra algorithm. So here for the routing we have another theorem which we validated in both of the setups, saying that we can compute the average number of hops in a hyperfractal, and the expression is a function again of the fractal dimension of the nodes and a fractal dimension of the relays. I'm going to refer you to the paper for the whole proof, but I can give you some hints. So it's easy to compute. We look at the number of hops that the packet has to do in its way from, let's say, the transmitter towards the receiver. We can compute using this lemma the average distance towards an intersection, because we have the process and the probability of having an intersection relay given by the hyperfractal process of the relays. Furthermore, as we've seen, we have the density of the nodes, which decreases as a function of the level of the street. So of course the preferred route will be the route with an h that goes towards infinity. But the problem is, as the h goes towards infinity, the probability of having a relay in the node, in the intersection, that allows us to come back towards the destination decreases. So we're going to be forced to add extra intermediate routes where the probability of turning is not 0. So I'm going to refer you to the paper for the whole proof, but let us make the observation that when the fractal dimension of the relays is 2, the optimal path length goes to 1 for a fractal dimension of the mobile nodes towards infinity. So we confirmed these theoretical findings also with simulations. So we vary the number of points for mobile nodes and both for relays for different values from 200 up to 1600. We validated for fractal dimension equals 3, but in other works, we work with other options as well. And we can see that by increasing the number of points, both in mobile nodes, both in relays, the fraction of total points in the giant components goes to 1, and the number of points outside the complementary, of course, goes towards 0. So let's look at this number of nodes outside the giant component. You see it's not a very clear going up function, but easily with the increase of number of points, the fraction of points outside the giant components goes towards 0, and furthermore, it follows the scaling law that we computed. So in this work, I presented you what we call a hyperfractal with a Poisson-Schott model, which has a support measure whose fractal dimension is higher than the Euclidean dimension. That's why we call it hyper. We have two hyperfractal processes. In fact, one is for mobile nodes, one is for relays. We show the properties of the giant component, which generates the connectivity of the network. We show the path length scaling, but we have still a lot of work to do on this model in computing typical metrics that we use in stochastic geometry, such as typical point, typical distance, thinning processes, and so on. So thank you, and I'm waiting for your questions.
question. Okay, your approach is different from what we presented in the first two presentations, but there are some connections. And when I heard about fractals, I imagined one of the applications that were in distant geometry where you need to find the conformations of proteins. You know, if okay, I didn't have in my presentation, but if you imagine a protein is done by helices, beta sheets, so they have regular patterns, and they can look like a fractal. I never imagine to consider this a fractal theory, but there can be some relationships.
I looked at fractals, okay, starting okay, more in the application field of wireless networks. But so fractal growth is a characteristic of the world, let's say. It's not only in wireless networks. It actually, there's a huge community working in biology and genetics rather than in wireless networks. But what I know that in proteins, what I've been reading is mostly using stochastic geometry and organization with the Voronoi tessellations. And of course, this brings us, we bring together the fractal geometry with the stochastic geometry, so to be really a nice approach for studying proteins, of course. Exponential growth, yeah. Exactly. So it's like each structure is just, yeah.
Volume of your lung, you won't be able to move. Is that a question? Thanks again.